Derivatives follow certain rules. I won't be proving any of them. It's too much work. But there's the power rule. If we have x to the n, then the derivative would be n x to the n minus 1. For example, for x squared, we had 2x to the 2 minus 1, or 2x to the 1, or just 2x. If we had the constant, not n, x to the 0, that's just 0 times x to the minus 1, I guess technically, but that's a 0. Doesn't really mean anything. We could do this for any number of x, n, 17. We could do 3 over 2, which could be written as the square root of x cubed. But, the same thing. 3 over 2 times x, 3 over 2 minus 1. And 3 over 2 minus 1 is just 1/2, so 3 over 2 times the square root of x. We could do negative. So negative 3 times x. Negative 3 minus 1 is negative 4. And we can rewrite that as negative 3 over x to the 4th. There are some more complicated rules. For example, if we have the product of two functions, let's say we have f of x is equal to f of x times g of x, then f prime, or the derivative of f, is f prime of x g of x plus g prime of x f of x. We can also make this a 3-term product, say something like that, and it'll become a little bit harder, but not much. Basically the same thing, but now we add the extra term. And then the derivative of h of x. But most of the time it's just going to be the 2 products. Sometimes it'll be 3 products. But what you do is you take the derivative of one and multiply it by the others, and so on for each term. Each term would get a derivative. Sometimes in math we'll get these nested functions, so we'll get like y is equal to f of g of x, for instance. Usually you'll start with like some argument, say like x to the 5th, and then we can make x like its own function. So it would look something like this. Something like that, or natural log of x squared sine of 2x plus pi, something like that. We can do exponentials. If we want to find using the derivative of this, it's called the chain rule. And the chain rule is we take the derivative of the outside function and multiply it by the inside function derivative. So for x plus 7 to the 5, we take 5 times x plus 7 and bring that number down to -1, and then multiply by the derivative of x, which is just 1, so that would just be 5 times x plus 7 to the 4. We can make it a little more complicated. We could say y is equal to x plus 7 to the 5, but now change that to the x squared plus 7 and raise that all to the 5th power. We can do that. It follows the same pattern. Y prime is equal to x squared plus 7. 5 times x squared plus 7 raised to the 4th times the derivative of x squared plus 7. And the derivative of x squared plus 7 would be 2x plus 0. So this would be equal to 5 times x squared plus 7 to the 4th times 2x. And doing a little rearrangement, y prime is equal to 10x times x squared plus 7 raised to the 4th. Just as we have the product rule and the chain rule, there's a rule called the quotient rule, which is when we have a function that is a quotient of functions, which can be written as a product of functions. That's not the inverse, that's the reciprocal. And we can find the derivative of this now by using the product rule and the chain rule. So we take the derivative using the product rule, g prime of x, h of x inverse plus g of x, the derivative of h of x inverse. Now the tricky part is taking the derivative of the, not inverse, sorry, the reciprocal of h of x. So the derivative of h of x raised to the -1 would be -1 times h of x and then times that by h of x to the -2. This is derivative. So we're left with the negative of the derivative of h of x, and then that's the squared. So then we have g prime of x over h of x minus g of x h prime of x over h of x squared. And this is almost looking like the textbook definition. Technically we need to combine this into one fraction, so what we do is we multiply this left side by 1, h of x over h of x. So we're left with g prime of x h of x minus g of x h prime all over h of x squared. And that's the quotient rule. Basically, if we're given a function, let's say e to the x over sine of x, we would plug in the values, not the values, but the derivatives and the actual functions into this term right here, this equation, where the numerator is g of x and the denominator is h of x. And that's all. Thank you for watching.